We have seen the notion of a subspace of a vector space, and then we looked at some 4 important subspaces of a space V f n and f m concerning an m by n matrix. So, what were these 4 subspaces? We had, if A is an m by n matrix, then on the n component side we had 2 subspaces, namely the range of A transpose, which was the same as the column space of A transpose, which is the same as the range of A, the row space of A, because the columns of A transpose are the same as the rows of A. On the other hand, on the f m side we had a range of A, which is the same as the column space of A and which is the same as the row space of A transpose. So, this is the first subspace on either side, and then the second subspace we had was the null space of A on the f n side and the null space of A transpose on the f m side. So, these are the 4 important subspaces associated with a matrix A, and most of the analysis to answer our questions depends on the analysis of these 4 subspaces. So, in order to develop the analysis, we should first develop some machinery or some techniques in the idea of vector spaces. So, to this end, we shall first look at the notion of the subspace spanned by a set S, which we have already seen. So, what we have is a vector space V over a field F. This is always, I keep repeating, is always the universe in which we work in, the vector space over a field F. Suppose we have a set S, finite set u 1, u 2, u r in V. Then we defined the subspace spanned by S to be the collection of all linear combinations of S vectors. The collection of all linear combinations of S vectors is called LS, and this we have seen is a subspace first, and it is a subspace that contains S, that is S is a part of the subspace, and not only that, among all subspaces that contain S, this is the smallest. So, the final clinch is it is the smallest subspace that contains S. So, given a finite set u 1, u 2, u r, the collection of all linear combinations of these vectors form the smallest subspace that contain S. Now, what do we do if S is an infinite set? What if S is an infinite set? Then we do not know how to take infinite linear combinations, because that might even in the first place lead to convergence notions which do not exist in a vector space. So, we have to avoid taking infinite linear combinations at this moment, and therefore, we will resort to only finite linear combinations. So, how do we do this? So, given a set S, consider any finite subset of S. consider any finite subset, let us say S tilde of S. Then we can look at L S hat, which is the subspace spanned by S hat, which is a collection of all linear combinations of the set S hat, because we already seen above that the moment you are given a finite set S, we can talk about L S as the collection of all finite linear combination. So, given an infinite set S, we look at one particular finite subset and we can talk about the subspace spanned by L S hat. Now, suppose we do it for all possible finite subsets of S. So, let us denote by F S the collection of all non-empty finite subsets of S. Then for every S hat in F S, that means for every finite subset of S, we can define L S hat. Now, we put them all together in a basket, what do we get? So, we get the union of all the L S hats where S hat is in F S, that is the collection of all subspaces spanned by all finite subsets of S. So, we take every possible finite subset of S and generate the L S hat corresponding to this and take the union of all these possibilities, we get a huge collection of vectors. We define this to be L S. So, when S is an infinite set, you take all possible finite subsets of S and look at all the possible linear combinations of this and we get L S. So, it is easily seen that L S is actually the collection of all possible, since we are going to take only S hat as finite. So, it is going to be all possible finite linear combinations of S vectors. Take only a finite number of S vectors and look at their linear combinations and do it over all possible finite sets. And it is easy to check that first S is a subspace and we keep on adding the usual adjectives. S is a subspace qualifying, namely containing S, that is the next additional property, and then among all subspaces that contain S, this is the smallest subspace. S is the smallest subspace containing S. Thus, L S in the case of infinite set has to be brought to ground level of finite set first and look at all possible finite subsets and look at all the possible subspaces spanned by them and take their union, and that is going to be a subspace, and that subspace is the smallest subspace that contains S, and that is called the subspace spanned by S. L S is called the subspace spanned by S. Now, it is clear that the above definition is the same as the original definition, namely if you look at this infinite way set where you generate all finite sets and from them you generate all the linear combinations and then take all of them together, you get L S. But suppose S was only a finite set and then you take only finite subsets of this finite set, and obviously S will be a part of F S and you already get L S here, and all the others are subsets of this. So, this definition will give the same LS in the case when we have finite sets. So, when looked at that way, this is a proper definition of LS for all possible sets, whether they are finite or infinite. So, it is clear therefore, that the definition LS equal to union S belonging to Fs of S hat of LS hat coincides with earlier definition when S is finite. So, now we can handle even the so called subspace spanned by an infinite set. The next important thing is we had this notion of linear independence. Recall that this notion also we had only for finite sets. We had the notion of LS only for finite sets. From that we generated the notion of LS for infinite sets. Now, we have so far the notion of linear independence only for finite sets. From that we are going to generate the notion of linear independence for infinite sets. So, recall if S equal to U1, U2, UR is a finite set, then in of course, V the vector space V, then we say S is linearly independent if any linear combination of this gives us the 0 vector. Since these are linear combinations, these alpha j's are from the field F. If any linear combinations gives the 0 vector, then the only way this can happen is all the coefficients are 0. This is the definition of what is meant by linear independence of a finite set of vectors. Now, when we have an infinite set, how do we define? So, suppose S is infinite is an infinite set in the vector space V, then what do we do? As before, we resort to picking finite subsets of this. So, if every finite subset of S is linearly independent, then we say S is linearly independent. So, definition: an infinite subset, an infinite set S in V is said to be linearly independent if every finite subset is linearly independent. So, let us say infinite, every finite subset of S. The moment you have finite subset of S, we have the notion of linear independence. So, we can check whether it is so. So, if every finite subset of S is linearly independent, then we say the set S is linearly independent. Let us look at a simple example. Let us look at the set F, the vector space, to be the space of all polynomials over the field F, that is the set of all those polynomials with coefficients from the field F. In this setup, let us consider S to be the set of vectors in V. What are vectors in V? Vectors are in polynomials in V. In this case, the vectors in V are polynomials with coefficients from F. So, we are going to consider S to be a collection of certain polynomials. The polynomials that we are going to consider are, say, 1, x, x squared, and so on. This is an infinite set. Take all possible polynomials with powers of x running through the natural numbers. So, x to the power of 0, x to the power of 1, x to the power of 2, x to the power of 3 and so on and so forth, we get an infinite number of polynomials, which means we get an infinite number of vectors in the vector space V, because the vectors in this space are all polynomials. So, let us consider this infinite set. So, this S is an infinite set in V. Is this linearly independent? To check whether it is linearly independent, we have to make sure whether every finite subset is linearly independent. So, what will be a finite subset? It will consist of certain number of powers of x. Now, if we take a certain number of powers of x and if you look at the linear combination, that will be a polynomial, and that polynomial will be 0 only if all the coefficients are 0, because the 0 polynomial is the one with all the coefficients as 0, and hence the answer is the S, because every finite set consists only of a finite number of powers of x, and hence as I said, any combination will be a polynomial, and that will be 0 if and only if all the coefficients are 0. So, therefore, every finite subset is linearly independent, and hence the original set is linearly independent. Let us look at another example. Take the interval 0 to 2 pi and consider the set of all continuous functions from I to R. That is, CIR, recall the definition, is the collection of all functions which map the interval 0 to pi and take real values. So, it is the collection of all real valued functions defined on the interval 0 to pi. On this vector space, consider the set of all these functions sin n x, where n runs through 1, 2, 3 etc. Previously, we looked at x to the power of n, where n ran through the integers. Now, we look at sin n x, where n runs through the integers. Now, this S is a linearly independent set in this vector space V, where our vector space is the collection of all continuous functions defined on the interval 0 to pi and taking real values. Why? What is it that we have to show that S is linearly independent? We have to show that any finite set is linearly independent. Consider any finite subset. Now, what do we mean by a finite subset of S? S consists of all sin n x's. So, we will be considering sum of the n's for finite number of the values of n. So, let us say S1 consists of sin n1 x, sin n2 x and so on sin n r x. So, we have a finite subset of S, where n1, n2, nr are integers. So, take any such finite subset. If we show that S1 is linearly independent, then we would have shown that any finite subset is linearly independent, and hence we would get S is linearly independent. So, to check if S1 is linearly independent, that is our main task. Take an arbitrary finite set and verify whether it is linearly independent. So, what do we have to check whether S1 is linearly independent? So, we start with a linear combination alpha 1 sin n1 x, alpha 2 sin n2 x and so on alpha r sin n or x equal to 0. 0 means the 0 function which takes the value 0 at all the points x in the interval 0 2 pi. So, to check if S1 is linearly independent, we look at a linear combination like this and see if all the coefficients are 0. Now, if this is true, we can multiply by sin njx and integrate. So, we will get sin n1x into sin njx plus etcetera plus alpha r sin nrx into sin njx is equal to 0. Now, if we integrate from 0 to 2 prime using the properties of sine, we see that the first term is 0, the second term is 0 because sine use the fact that integral 0 to 2 pi sin kx into sin Lx dx when k and L are integers is 0 if k is not equal to 1, if k is not equal to L, and pi if k equal to L. If we use this property in this integral, every term will vanish until we hit nj, where we will get sin squared njx, and that will be pi. Sin squared njx will be pi, and so we will get alpha j pi equal to 0. But since pi is not 0, that will say alpha j equal to 0. So, for every j, if you do this from 1 less than or equal to j less than or equal, we get all the coefficients to be 0. So, therefore, S1 is linearly independent. Since S1 is an arbitrary finite subset of S, S is also linearly independent. Thus, every finite subset of S is linearly independent, hence S is linearly. So, thus the notion of linear independence on finite sets comes from the fact that every subset of S must be, every finite subset of S must be linearly independent. So, an immediate remark we must note is that if S is infinite and linearly dependent, what do you mean by linear dependent? If it is not linearly independent, it must be linearly dependent. Not linearly independent means what? Negation of linear independence. Linear independence means every finite subset is linearly independent. Negation means at least one finite subset will not be linearly independent. That means what does that mean? At least one subset. What sort of subset? Finite subset. At least one finite subset of S must be linearly dependent. That is the important property of linear independence and linear dependence when we are talking about infinite sets. So, now we have extended the notion of the subspace spanned by S to even infinite sets. We extended the notion of linear independence and linear dependence to sets which are also infinite. So, therefore, we do not have to worry about finite and infinite sets, but it makes a lot of difference when the sets that we are going to deal with finite or infinite. So, now we will look at some properties of linear independence and linear dependence. We shall look at some very useful important properties which will come in handy very often in our analysis. The first property. So, we have a vector space V. Suppose we have a subset S which is linearly independent. So, suppose S is contained in V and S is linearly independent. Again we repeat that in the background we always have a vector space V over F, that is our universe where all these discussions take place is in a vector space over a field F. So, suppose I have a vector space V and I have a subset S which is linearly independent. So, this S is linearly independent. Now, look at a non-empty subset of S. So, we have S1 contained in S, S1 non-empty. What can we say about S? Is S linearly independent? Is S1 linearly independent? So, I have a linearly independent set, inside that I am taking a subset, will that subset also have the same property of linearly independent? Suppose not. What does that mean? This means this set S1 is not linearly independent. The moment S1 is not linearly independent, it must have a finite subset which is linearly dependent. So, this means S1 has a finite subset S2 which is linearly dependent. So, let us get back to the picture. We had linearly independent set S and inside that is sitting a subset S1. This subset S1 is such that inside that is a set S2 which is linearly dependent. Now, S2 is sitting inside S1 and therefore, it is also sitting inside S. Therefore, S2 is a finite subset of S and therefore, S2 is a finite subset of S which is linearly dependent. So, what this gives is that this implies S2 which is contained in S1 is contained in S and therefore, S2 is a finite linearly dependent subset of S. Now, this says S cannot be linearly independent, because if S were linearly independent, every finite subset must be linearly independent, but here we have a subset which is linearly dependent and hence S cannot be linearly independent. This contradicts the starting point that we had started with a linearly independent set. Yes, we started with the linearly independent set. Yes, and assuming that S1 is not linearly independent, we came to a wrong conclusion that the original set was not linear. Hence, S1 is also linearly independent. So, what is the conclusion? The conclusion, the first important property of linearly independent set is any non-empty subset of a linearly independent set is linearly independent. Subsets of linearly independent sets are linearly independent. So, it is like a hereditary property, because he is sitting inside linear independence, he possesses automatically that gene of being linearly independent. An analogous property is that if we start with a set S which is linearly dependent, anything above that must be linearly dependent. So, S linearly dependent, S1 is a superset of S, implies S1 is linearly dependent. Because if S1 were not linearly dependent, it will be linearly independent. If it were linear independent, anything sitting inside must be linearly independent. Therefore, S must be linearly independent, which would contradict the fact that we started with a linearly dependent set. And hence, any superset of a linearly dependent set is. So, conclusion, is that any superset of a linearly dependent set is linearly dependent. That is an analogous or dual property of the previous fact that any subset of a linearly independent set is linearly independent. Now, let us look at a linearly dependent set S. So, suppose I have a linearly dependent set S. What does that mean? A set is linearly dependent mean there will be a finite subset which will be linearly dependent, because if every finite subset was linearly independent, then the set S would have become linearly independent. So, S linearly dependent implies there exists a set S1 contained in S such that S1 is finite and S1 is linearly dependent. So, every linearly dependent set must possess a finite linearly dependent subset. So, here is this is the set S1, U1, U2, UR. So, I have a set linearly dependent. The moment it is linearly dependent, it must contain a finite subset S1 which is linearly dependent. So, we are writing S1 as U1, U2, UR. Now, since S1 is linearly dependent, what does that mean? A set is linearly dependent, finite set is linearly dependent. If we can write a combination, linear combination which gives 0 vector without all the coefficients being 0. So, linearly dependent, there exists alpha 1, alpha 2, alpha r, not all of which are 0, such that alpha 1 u1 plus alpha 2 u2 plus alpha r ur is the 0 vector. Now, we look at this alpha 1, alpha 2, alpha r, all of them are not 0. So, we keep going seeing which is the last non-zero alpha. It may be alpha r, or maybe alpha r is 0, but alpha r minus 1 is not 0, or it may be that alpha r is 0, alpha r minus 1 is 0, but alpha r minus 2 is 0. So, we go and find which is the last index for which alpha is not 0. So, let alpha j be the largest index for which alpha j is not 0. We know that not all of them are 0. So, we keep on going until beyond which there is nothing is available, everything is 0. So, j is such that alpha j is the largest, the longest among them, beyond which nothing else is non-zero and everything else is 0. This means alpha j plus 1 must be 0, because j is the largest index for which alpha j is 0. So, therefore, alpha j plus 1 is 0, alpha j plus 2 must be 0, and all the way up to alpha r is 0, because j is the large. If j is r, then everything is not, alpha r itself is not 0. So, now we have what does that mean? Look at this starting point. Suppose u1, u2, ur are linear independent, then we must have a combination like this. Since beyond j, alpha j's are all 0, this sum will terminate at alpha j uj. So, we get alpha 1 u1 plus alpha 2 u2 plus alpha j uj is theta v, and alpha j is not 0. If that is the case, we can write uj as equal to beta 1 u1 plus etcetera beta j uj, where beta j is minus alpha, let us put it beta I is minus alpha I by alpha j. This should be beta j minus 1, u j minus 1. We take u j to one side and all the others to this other side. And this is possible because alpha j is not 0. In a general field, division means multiplying it by alpha j inverse. So, this is actually minus alpha I into alpha j inverse, the multiplicative inverse of alpha. This means u j is a linear combination of finite number of vectors in S. So, let us go through it what we have done. We have taken a set S and we assumed it is linearly dependent. So, we have a linearly dependent set and therefore, we got a finite subset and therefore, we got a vector which is a linear combination of finite number of vectors. So, the conclusion is if you start with a linearly dependent set, there will be at least one vector which is a linear combination of finite number of vectors in S. There will be at least one vector which is a linear combination of finite number of vectors. So, the conclusion of this discussion is that if S is linearly dependent, there exists at least one vector u in S such that u is a linear combination of a finite number of vectors in S. So, this is the third important property of this linear independence and dependence. The first one was that every non-empty subset of a linearly independent set is linearly independent. The second one was the dual result that every superset of a linearly dependent set is linearly dependent. The third is that whenever you have a linearly dependent set, at least one vector is a finite linear combination of the others. Now, let us look at the specialization when we look at a finite set. So, suppose S equal to u1, u2, ur is a finite linearly dependent set. Now, since this is a linearly dependent set, we must have a linear combination which is 0 without the coefficients being 0, like what we have just now done. So, there exists alpha 1, alpha 2, alpha r, not all of which are 0, such that alpha 1 u 1 plus alpha r u r is equal to theta v. Once again, look at the largest index for which alpha j is not 0. So, let j be the largest index such that alpha j is not 0. Therefore, as before, we get alpha 1 u 1 plus alpha j u j is equal to theta v. Again, as before, we get u j is beta 1 u 1 plus etcetera beta j minus 1 u j minus 1, where beta I is minus alpha I alpha j. This calculation is exactly the same as we did before. Now, what we get is we have this set of vectors u 1, u 2, u r, we are arranging them in that order. So, we have finite set of vectors which are linearly dependent, which are arranged in a sequence u 1, u 2, u r. If we do that, then there is a vector u j which is a linear combination of all the previous fellows u 1, u 2, u 3, u j minus 1. So, there is a vector u j which is a linear combination of all the preceding vectors. So, what is the conclusion? The conclusion is that if S equal to u 1, u 2, u r is a finite linearly dependent set, then there exists a vector among these which is a linear combination of all the preceding vectors. Okay, so, if you have a linearly dependent set, a finite number of them arranged at the first, second, third, fourth and so on, somewhere along the line there will be a vector which is just a linear combination of all the earlier ones. So, that is another important property. We will use these simple facts very often. The next, we keep expounding this idea further. Suppose we have again a finite linearly independent set, I am sorry, the dependent set. Suppose linearly dependent and finite. Now, what does our analysis just now says? It says that if one of them must be a linear combination. So, we are interested in looking at, we are interested in this, the space spanned by what is it that we can build. Now, if any one of these vectors u1, u2, ur is a 0 vector, it is no way going to help us in the building blocks, because whatever multiple of 0 you get, you are going to get 0, and whatever vector is added to 0 vector, you are going to get the same vector. So, 0 is not going to add anything to your building process. So, without loss of generality, if there are any 0 vectors, we can throw them out. So, without loss of generality, assume all these vectors as non-zero vectors. So, we have a finite set of vectors u1, u2, ur, they are non-zero and they are linearly dependent. So, here is a finite set of vectors which is linearly dependent. Now, our analysis just now says whenever you have such a set, there must be a vector which is a linear combination of all the preceding fellows. There must be a vector among these which is a linear combination of the preceding vectors. Now, we do not know which one it is. Well, it may be that u5 is a linear combination of the previous vectors, u22 is a linear combination of the previous vectors, u13 is a linear combination of the previous vectors. So, there are many vectors. We know that there is one. There may be many vectors which are linear combinations of the previous. There could be 1, there could be 2, there could be 25 vectors which are linear combinations of the previous one. So, we do not know. All we are assured by the previous analysis is that there is at least one vector which is a linear combination of all the preceding vectors. So, now what we do is we look at this set S. Let me first explain what we do. Let us look at the set S. What I do is I start moving from the left. Can u1 be a linear combination of the preceding fellows? No way, because u1 is a non-zero vector and there is nothing previous. So, it cannot be expressed in any term. So, u1 is not a linear combination of the preceding ones. It may be that u2 is a linear combination or maybe not. So, what I do is I go from the left. The moment I hit a vector which is a linear combination of the previous ones, I stop. That means, I look at the first vector from the left who is a linear combination of the previous fellows. Suppose I have a vector here which is a linear combination of the previous fellows, then I strike it off. Let me do this elsewhere so that it will be more clear. So, I have u1, u2 and so on, ur, then I go from the left. I keep searching for a vector which is a linear combination of, I see u2, are you a linear combination of u1? No. Then I go to u3 and so on. Then I hit the first vector which is a linear combination of the previous vectors. I delete that fellow. I just remove him from the set. Then what I have is r minus 1 vectors which is a subset of the original set S, because one of the vectors from the S has been removed. Then again after removing whatever is remaining, I continue this process again. Now again I search from left to right. Now nothing before this can be a linear combination of the previous fellows, because this was the first vector that came about as the linear combination of the previous vectors. So the next, if at all there is any other vector, it will come later. So suppose we hit another vector which is a linear combination of now all the previous vectors with this removed. This has now been removed. So with this removed, if this fellow is a linear combination of all the previous, then we remove that. We continue this process. When we continue this process, since this is a finite set, it will eventually ultimately end giving us a finite subset which is now linearly independent, because nothing is a linear combination of the previous fellows. So how do we do this? So therefore scan from the let, remove the first vector that you get from left, which is a linear combination of the previous vectors, repeat the process on the remaining subset. After a finite number of, because we are with a finite set, this has to terminate, this process has to terminate, because we keep moving to the right and there is only that much space to the right, it ends at UR. So they cannot move beyond UR. At each stage we remove one vector, there are totally only R vectors, you could not have removed more than R vectors. So therefore after a finite number of steps, we get a set S1 which is strictly contained in S, such that now whatever was removed was a linear combination of the remaining fellows. So therefore they are not going to produce anything new in the spanning, the LS1 will be the same as LS, and S1 is linearly independent. So therefore the conclusion is that if you have a finite set S which is linearly dependent, then the subspace spanned by S can also be spanned by a subset S1 which is linearly independent. So now let us summarize. Conclusion: if S is a finite linearly dependent set, then there exists a subset S1 of S such that 1 S1 is linearly independent and S1 also spans the same as LS. What we are doing is a linearly dependent set has a lot of redundant information. Systematically we are trying to remove all the redundant information and retain only the relevant pure information which comes from that linearly independent subset S1. So given any linearly dependent set S, there is a finite linearly dependent set S, there exists a finite linearly independent subset of S such that it spans the same space as the original fellow. We shall look at one more small property, which this was number 5. So the next one is something which we will use again. Suppose we have vector space V and we have a subspace W, and inside that subspace we have a linearly independent set. This is linearly independent. So we have V vector space W subspace of V and S contained in W is linearly independent. So, we have considered a subspace of V inside which we have a linearly independent set. Now, suppose W is a small part of V, there is a lot of space left outside W. In this space, suppose I go and pick up a set S1 which is linearly independent. So, S1 is contained in V, but not contained in W, it is sitting outside. So, S1 is in V, but not in W, and S1 is linearly independent. Now, it is not difficult to verify that S union S1 will also be linearly independent in V. This implies S union S1 is linearly independent in V. We shall leave the verification as an exercise. So, we will simply write why. We just verify, it is a very simple process. Suppose it is not linearly independent, and then you will get a contradiction. So, if you take a subspace and inside that subspace you take a linearly independent set, and you pick up a linearly independent set outside. So, you take a linearly independent set inside W and you take a linearly independent set outside W, the two together will be an independent set in the V. So, in particular, suppose we take V and we take a true subspace W. So, W is contained in V and W is not equal to V, and we take, well, we can take in arbitrary. So, we will take a S inside that linearly independent. So, S contained in W linearly independent. So, we have vector space V, inside that sitting a proper subspace W, inside that is sitting a linearly independent set, and since W is not equal to V, there is something outside. So, let us pick a vector x which is sitting outside. So, x belongs to V minus W. There is a vector x which is sitting outside W, because we are assuming that W is not equal to V. In that case, can x be 0? The answer is no, because every subspace must contain the 0 vector, and so the 0 vector must be sitting inside this W. Because theta V belongs to W. Because W is a subspace, it must contain the 0 vector. So, x cannot be the 0 vector, and therefore, the set S1 consisting of only that vector is linearly independent. Now, we have a linearly independent set outside W and we have a linearly independent set inside W. Therefore, by a previous analysis, these two union must be linearly independent. Therefore, S union S1, that is S union X, is linearly independent. So, in other words, if you take a subspace and inside you have linearly independent vectors and you pick some other vector from outside and append it to your linearly independent set in W, it still retains its linear independence. Okay. So, if you take a vector x outside W and append it to the vector to the original linearly independent set, and it remains to be linearly independent. This is a very useful thing, and we will use it in basis analysis. The next important notion that we will be introducing is that of a basis. The name suggests it is a fundamental notion, it is a basis of many of our analysis, which we will look at in the next lecture.